Hello all, just doing a quick video on 13.1, which is the first part of periodicity HL. So let's get into it. So we are going to be looking at the first row D block elements. Just like for the periodicity review video I did, and I've just grabbed one for myself, it might be a good idea to get a periodic table so you can have a look. So we're going to talk about what transition elements are, why zinc is not considered a transition element, and some of the properties they have and why they have those properties. So there is a lot of information in the data book. So I will be referring to some of those tables as we move through. So just apologising in advance, there might be a bit of a break in the recording between this and my next slide, because I realized I started talking about transition elements but didn't actually explain what we mean by a transition element. So the definition of a transition element is in at least one of their oxidation states, they've got an incomplete D subshell. So if you remember from our electron config, copper was the exception to the rule because it was argon 4s1 3d10. So that's copper. Copper plus is argon 4s1, but copper 2 plus is argon 3d. Oh, sorry, I somehow lost. Copper plus is 3d10. Copper 2 plus is 3d. No, I'm sorry, my brain is just not working today for some reason. So this incomplete D subshell has to be there. So for example, one of the things that I mentioned, and I need to go back to my pen, is that zinc is not considered a transition metal. So zinc is argon 4s2 3d10, but zinc only forms zinc 2 plus, which is argon 3d10. So even when zinc becomes the ion, it's got a full D subshell. Therefore, not transition. Okay, so now that I've hopefully clarified a little bit about what transition elements are, let's continue on. So variable oxidation states. So you probably remember from when we were doing like balancing and redox, if you've got something like Fe3 plus, I can add an electron to that and it can form Fe2 plus. There seems to be some sort of option for transition metals that a lot of the others don't have, where these things can have multiple transition states. For example, copper forms the standard 2 plus ion, but it can also form a copper 1 plus. Why that is because those D block electrons, those D subshell electrons, because those electrons are so close together in terms of their energy levels, the ionization energies to move between a 3+ ion and a 2+ ion, those electron affinities and ionization energies are super close together, which decreases the amount of energy that you need to give. There is a table in the data book that has the common oxidation states for the transition metals. You're not expected to know these off the top of your head. You're expected to know that these guys can have variable oxidation states, but you're not expected to know exact numbers. So one thing that these transition metals do when they are in solution, so I'm just going to call it M+. Because our transition metals have those positive charges, what will tend to happen, and I'll switch to blue, you've got your oxygen, hydrogen, hydrogen. So looking at water, there will be an attraction when my metal ion is in solution. But it's more than that. So it doesn't have to be water that's attracted. It could be an iodide ion, or it could be an ammonia. Now, I am going to discuss this more in part 2, but these complex ions have different colours depending on 2 things. 1, the identity of the metal, and 2, the identity of the ligand, the thing that is attaching to my metal ion in solution, for reasons that I will get into in half an hour my time, whenever you watch the second video your time. So coloured complexes. Now, in the 3D subshell, there are 10 electrons, which means that there have to be 5 orbitals. Now, something really interesting happens with those 5 orbitals. They do something called orbital splitting, which again, more detail later. But because these 2 energy levels are really close together, if an electron falls from this orbital back here, it can release some light energy. Now, because those energy levels are so close, instead of like when you're looking at the hydrogen series, we've got either UV or like I think it's UV or high-end visible. I can't remember just at the moment. As I said, my brain's failing me. Because the mini transition within that D subshell is so close, the energies that are released or absorbed are in the visible spectrum. So depending on what I have my copper solution, so whether it's a copper nitrate solution or a super concentrated copper chloride solution, my copper ion gives different colours because of basically the distance between these 2 energy levels. So if those energy levels are slightly further apart, it takes slightly more energy, which means that the colour that's being produced might be slightly closer to green or even blue. We are going to discuss this at length next time, and I'm also going to talk about some of the ligands, so some of the things that attach to that metal ion. So I think I showed you this picture last year. It is from the website Compound Chem, who do some really beautiful visualizations of chemistry concepts. So here is a hydrated, so my only ligands are water, And so this is just seeing what the effect of changing out the charge on that metal ion is on colour. So chromium can form +2, +3 and +6. +6 has a very stereotypic orange colour. Copper we're used to seeing as blue. Iron you're probably used to like this rusty orange colour. But if you force it into that +2 state, it does form actually quite a nice sort of pale greeny colour that I think is quite pretty. But that is just because of the energy that is being released when those electrons move from one energy level to another. Alrighty, so there is a really good explainer there. Check out this website. It does have really beautiful visualizations and like chemistry posters. So, as I've discussed, for example, if I take Fe2 plus, it can form Fe3 plus an electron. Why that's useful? If you have a chemical reaction that involves moving electrons around, so for example any redox reaction, having something there that is able to donate and accept electrons quite readily is super useful. I would normally at this point do a demo in class looking at a transition metal catalytic reaction. I will have a look and see if I can find a video of it, in which case I'll link that in the description. Otherwise, it might be something that we have to do once we're back at school. So, because my transition metals are able to donate or accept electrons pretty readily, they're often a really good place to act as a transition state. So taking your electrons off your ion 2, donating them to a product, one of your reactants, and then one of your other reactants donates back the electron to our ion. Because of the flexibility in transition states of our transition metals, because of the flexibility in oxidation states of our transition metals, that makes them really flexible at being able to change their oxidation state, donate or receive electrons, which can make it easier for other reactions to proceed. Okay, so there are 3 types of magnetism. The first type is what is called ferromagnetic. Now, as the name suggests, your Greek, Latin, it's one of the two, I can't be bothered looking it up. As you might work out from the name, this is the type of magnetism that we find in some samples of iron, but also sometimes nickel and cobalt, though not as strongly in those second two. So this is a permanent magnetic attraction that is basically caused by electrons unpaired lining up in parallel. And I think I've discussed this before. Yes, I did, in the context of why we've got our spin. So, whenever I've got a moving electric charge, it generates a magnetic field. Now, electrons are tiny, so the field they generate is tiny. But if I have billions times billions times billions of these things, all pointing in the same direction, those tiny little magnetic fields add up. So if something's ferromagnetic, it is a permanent, so it's permanent, unless I melt down my iron, for example. And whether or not it's in an external magnetic field. So it remains magnetic even in an external field. And it comes back to the unpaired electrons spinning in parallel. So unlike our ferromagnetic, which are permanent, we then have paramagnetic. So this para means the same thing as paramedic. So para means associated with. Oh, be good if I could spell associated. So paramagnetic fields only happen in association with an external field. Again, it's because of those unpaired electrons, and it strengthens the field. Strengthens. So a paramagnetic item has those unpaired electrons, and when exposed to a pre-existing electromagnetic field, it makes that field stronger, as opposed to diamagnetic. So that is because of paired electrons. So if a substance has all or mostly paired electrons, what happens is that when an external field is applied, it's opposed. So diamagnetic substances make the field weaker because those paired electrons oppose that magnetic field that's being applied. Again, all of these different magnetic properties come down to how the electrons are arranged. So are those electrons independently creating a magnetic field in the case of ferromagnetic? Do they strengthen a magnetic field when exposed to it, which is our paramagnetic, or do they oppose it? So the way I remember it, so ferromagnetic is what iron magnets do. Paramagnetic, and I literally ran through how it works. I think of like parallel. So if two things run in parallel, they're running alongside each other. It's also where we get paramedic, so next to. Dia, I think, deducts. So it's opposing or deducting from that external magnetic field. Of course, I'm saying external magnetic field. I could equally be saying electromagnetic field. They are intertwined forces. Okay, so in this video, we've talked about variable oxidation states, complex ions, coloured compounds, and catalytic and magnetic properties. I've talked about what is a transition metal and why zinc is not one. I didn't talk about this so much, but in all of our transition metals, we can always, let me just switch to my pen, we can always remove those 4 s2 electrons. So all of our transition elements show a +2 oxidation state. So I didn't talk about successive ionization energies. I will do that in our Zoom call. I explained the attraction between within a complex ion. I didn't talk about deduction of overall charge. I talked about magnetic properties, and I explained that all of that was in the data book. Thank you so much. Have a great rest of your day, and I'll see you next time. Bye.